my distinct pleasure today to introduce our invited speaker, Alán Aspuru-Guzik, who's a professor of computer science and chemistry at the University of Toronto. Received his bachelor's in science and chemistry from the National Autonomous University of Mexico, and later a PhD in physical chemistry from the University of California at Berkeley. He's both the director of the Acceleration Consortium, which is an effort by the University of Toronto to develop AI-guided self-driving laboratories, and the AI chair of the Canadian Institute for Advanced Research. Alán's research currently focuses on the intersection of chemistry, AI, and quantum information science, and he's here today to talk to us about how to do impactful research in AI for chemistry. So please take it away whenever you're ready.
Hi, everybody. Can you guys hear me well? I hope so. Well, I decided to change my talk at the last minute because I just gave this talk as part of a Faraday discussion as the Spears Memorial Lecture. And I think it was very well received there. And I thought that the audience of the Materials Project would like to hear something a little bit more general. Okay. So let me tell you a little bit about what I want to talk about today. And it's, okay, so all of us are doing research in AI for chemistry, but how can we make it actually impactful? What are the parameters that I think and my group thinks make it powerful? And I will use examples from my own research group as guiding light. I assume I have 45 minutes plus question or something like that. How much time do I have?
Yes, that's exactly right.
Okay, I'm accepting a bunch of people into the room. I assume you're accepting them. Yeah, so the paper is just right now online. It's accepted online. You can see it there. And it's kind of weird to be first author on a paper, but I basically wrote the kind of like the main idea of this paper, all the sections, then my group helped me finish it off, right? But basically, this is kind of like how my brain right now is organizing AI and material science, of course, with the combination of all the amazing brains of all the students and postdocs in this, and former group members in this list of authors. So what I want to talk about to you is that machine learning for chemistry and material science is very different for a lot of us, right? Like if you were actually thinking about what does it mean, many people tell me things like, oh, I just came up with this force field, and now because I have this force field, I can attack all of chemistry. And I kind of laugh at them, right? Because they really don't seem to understand the multi-scale nature and the complex nature of chemistry and material science, right? There's no way we can have a universal model that can capture absolutely everything in our discipline, right? So it must be different models for different tasks. And they all are going to interact with each other in more and more powerful ways, right? So the first thing that we want to think about then is a taxonomy of how this works, right? What would be the functional taxonomy of how machine learning could meet chemistry? So my group and I came up with this kind of figure, and I think this figure is a figure that will allow us to think about machine learning in chemistry in an organized way. So obviously we have foundational models as a kind of like a potential unifying model that will capture all of these things. As I said, I doubt there will be only one model, and we'll have a lot of models glued with each other in late fusion stages, which I can describe maybe later. And then, of course, there are very interesting structure-to-structure problems, like how to synthesize something, right? But also how to analyze something is a spectral prediction problem. The opposite is true from analysis to structure. I just saw a paper from MIT just announced yesterday that goes from powder X-ray to structure, right? That's a very interesting problem, an inverse problem that can be solved in the characterization. As well with simulation, right? Many people, as I said, are the force field kind of jocks and people that believe that the only thing that machine learning is structure to physics, which I believe is much more. You can, of course, imagine extracting properties, and what I'm very excited about always myself is the prospects of inverse design. So anyway, these are kind of like the map. If you are working on machine learning from chemistry and material science, and this map does not cover what you are doing, please let me know, because we still can update it and think about this map in different ways. So something that we can all think about is, let me try to hide this floating menu controls here. Okay, so what are the methods in our toolbox and what do they apply to? Okay, so on this column, you can actually see all the chemical problems that we could think about. For example, in drug discovery, the problem of docking, right? Or for example, we recently had a paper in the archive about the statistical mechanics problem of transition path sampling, right? You could also think about, the people that think about quantum Monte Carlo neural wave functions. And as you can keep going down this list, you can see that actually different types of different types of machine learning problems are needed, right? So most of the people, and actually many of us started in the view that the only thing that you do in machine learning is regression, right? So X to Y. And when you talk to like a, not so sophisticated person, they usually, that's what they think machine learning can do, right? More and more people are starting to learn about generative modeling, but in general, people think that that's what machine learning does, right? Generative modeling, of course, on the other hand, draws samples from a distribution, and obviously distributions such as all the possible materials or conditional distributions, all the possible materials that have certain properties, for example, are extremely important for our field. Sampling, obviously, generative model and sampling are actually related to each other, but they're not exactly the same. But here we're really talking about sampling from the probability distribution of a molecule, okay? And sample statistical mechanics, right? So how to use machine learning for StatMech. And then finally, obviously, I work a lot on problems where also they use gradient-based optimization for parameters. For example, you could, in principle, have simulation algorithms that are differentiable, right? And my group has done work on that, for example, for how to make a differential Hartree-Fock algorithm. And then black box optimization is more and more important for us, for example, in the context of Bayesian optimization or mandate optimization that are more and more used in the fields of process chemistry. Finally, obviously, a lot of people are fascinated by the LLMs, and agentic methods are actually very important to make our systems more intelligent. And I have actually worked on this, both in the context of my research group, but also a new startup that we launched called Axiomatic AI. Okay, so, but if we want to talk about AI in chemistry, probably we want to start where it started, and we can think about, say, cheminformatics, right? So a lot of you might find out that a lot of the most foundational computational algorithms and methods that we always use, for example, molecular dynamics, quantum Monte Carlo, etc., all of them have the roots all the way down to the 50s, okay? Also molecular electronic structure, by the way. And the reason is obviously the popularization of the digital computing machine. So it's not surprising that in that decade, Ray and Kirsch actually write about the challenge of representing molecules with strings, right? Or with some sort of text-based representation to classify chemical space, right? And of course, the same thing can be done for material science. And these are the kinds of things that I think are very important for cataloging the chemical space, right? So my own group's journal started, okay, in terms of this historical representation of how to come up with cheminformatics is when we were using at the time a lot of fingerprints and then mounting neural networks on this fingerprint representation. Okay, these are very simple bit string representations of molecules that contain hashes of basically elements in the next nearest neighbor and the next nearest neighbor. So now this is perhaps my second or third most cited paper, probably about 4,000 citations or almost there. This paper kind of started the idea of, okay, let's actually, instead of having this kind of discrete thing, make it soft-maxed so it's differentiable, and also add weight matrices in between, right? And that's basically a graph convolutional neural network. So in this paper in Europe, we actually started the kind of cottage industry of graph convolutional neural networks. It became then the mesh spatial neural networks. And then, of course, many people in material science are working on making these things equivariant and all that stuff, which I will discuss later why equivariance and these things might not necessarily be as needed or necessarily as scalable as other simpler approaches. And this is going to be an interesting part of this talk. So if you just want to do the first simple task of structure to property, or in other words, forward prediction or regression, I think it's important that all of us in this room probably are aware, but many people are not, of the actual practices, right? That's the actual practices of of how to get this done, right? So you usually want to be very careful to make the regressions correct, right? You want to have validation sets, training sets. You want to think about your splits, either a holdout split, which is, pretty good, or you can do validation split, or cross validations and so on, right? So you kind of want to think about how are you going to do your data splitting, what are going to be your features, and then optimize your model, right? So in the review paper that I have over there, we have some discussion about kind of good practices about how to do this. Okay, so this is a structure to property problem. So this is kind of like an oldie but goodie where we actually did that, right? So this is one of the earliest papers, and together with, this is a materials project seminar, so some of the seminal work of Gerd Sieder, Christine Persson, and many others. It was around the same time that we were already thinking about organic light emitting diodes, right? In this particular case, we generated a library of about 1 million organic light emitting diodes, and then down selected to about 30 that were synthesizable and tested. And if you actually see kind of like the workflow there, this is a workflow that uses forward prediction and then filtering. So it's not an inverse design workflow, but it actually allowed us to make state-of-the-art OLEDs back then. And obviously, this is kind of like one of the kind of foundational papers that people kind of based all materials discovery work on nowadays in terms of, okay, what are the type of things wants to do? And we even have a crowdsourcing where we call it molecular Tinder, where people were actually trying to see if a molecule was synthesizable or not by voting, okay? Interesting enough, there's been tons of work now about synthesizability of molecules since then. So now, okay, forward prediction is nice, but of course, many of us love generative models. I would like to say that, generative models are nice and sexy, but sometimes they are like mermaids, okay? And many students and postdocs like to gravitate towards the fanciest generative model, diffusion or this or that. And my group does that too. It's totally fine. But sometimes a pretty well-designed genetic algorithm can beat everything. As I'll show you later, our own Janus algorithm is extremely competitive, and it's just a simple genetic algorithm inspired by ideas from parallel tempering. And if you actually throw a genetic algorithm against some of these generative models, you actually see that their performance can be very similar or better. So as I will talk later on some of the other recommendations, don't get too fixated in the model. A generative model ultimately has many different tricks to represent a distribution, and what matters is sampling from it. And this is where we were lucky enough also to be one of the first ones in the field to actually introduce this idea of autoencoders for molecules. Okay, that's also one of our most cited papers. And since then, what was very exciting about this is that I was immediately contacted when that paper was in the archive by Alex Shaboronkov from In Silico Medicine, which had been using autoencoders in his company, started working on them for drug discovery. So together we did like a campaign, right, which lasted about 45 days. Obviously, it was prepared before. But in that campaign, we actually used Gushi Aptech, which are basically contract research organization, to actually help us do synthesis and then testing in animals and rats of the compounds that were generated with the AI. And this was perhaps the first publication on AI discovered lead candidate for a drug. Since then, several companies, perhaps all the top pharma companies, have AI in drug discovery program, and there's many biotech companies and also companies, established companies that have, like AstraZeneca, that have drugs in the pipeline that were generated with AI in any of the different stages of development. Okay, so this is actually really cool, right? This is actually a field that can we witness start, and now it's actually flourishing. So can we do this for material science, right? I mean, we're in a material science seminar. Is this possible, right? So continuing on our kind of like overview of different types of machine learning, it will be hard to pass, obviously, the idea of the structure to physics problem, right? Of course, the idea of making machine learning potentials. The idea, obviously, is that the cost is equal to force fields, but the accuracy is as good as ab initio methods, right? That would be actually the goal of any person that is developing machine learning force fields. And obviously, things started with local descriptors, then local descriptors, then we can add long-range interactions, which is very powerful and important. My own group has had experience with long-range problems with force fields, and we're actually working. I don't develop force fields usually, but for our own needs, we needed to actually start working and correcting some of these popular force fields for the long range. And obviously, again, our good old friend, message passing, that is a cousin of the graph convolutional neural networks, is basically now one of the state-of-the-art methods to actually build these algorithms, right? So that's on the side of force fields, but there's also a very interesting structure to physics type of problem, which is, can we actually simulate Schrodinger's equation? Right, and there we have different approximations, right? So what we just talked about here before was the machine learning potentials. This is an example of a, say, reactive potential for a molecule with two electronic states. So all these force fields usually are just in the ground state, but obviously here we're trying to feature also the fact that obviously for molecules, but also for materials, you really want to have the entire energy spectrum. But obviously, can you actually take our good old correlated electronic structure methods, DFT, etc., and enhance them with quantum chemistry, ultimately trying to have the accuracy of a correlated method for less, right? But now we're already talking about much more detailed calculations than the force fields. And finally, the full ab initio methods like, again, quantum Monte Carlo done with machine learning, neural wave functions, are probably at the pinnacle of complexity in terms of how much computer time and also model cost you might need to actually represent a molecule like that. But then you will be able to, for example, simulate the exchange correlation whole of a molecule or something interesting like that. So I think this is kind of like the level of structure to physics that we want to think about. So now I want to start jumping into some of my recommendations. Okay, again, this talk is about recommending things to you, right? Like what are good things that you could do in machine learning for chemistry and material science? And this is kind of like a Canadian Inukshuk, okay, live in Canada. So I want to argue that data is the most important thing. Then the representation of the data, then the model, and the evaluation. And I would actually like to argue that the model and the evaluation are probably equal in terms of importance, okay? So therefore, really, you don't want to start focusing on the model, okay? If you guys are focusing on the model, I think you're going to just be marginal to the community, right? It's more importantly to think about how to have or generate new molecular materials data. Then think about the data representation. And then finally, what is going to be the model you're going to choose and the evaluation, okay? So data. I argue the one that generates the data has the power to discover, okay? So if you have a robot like we have, or I guess Gerd has, and many other people now have robots that actually generate data from material science, right? You're going to be able to actually optimize on that data and in real time build a self-driving lab that uses that data. So that's, I think, to me, is the pinnacle of materials discovery. If not, you could generate a lot of digital data, as we'll discuss later. But I think data is the most important piece. So this is where I'm gonna tell you about a project that was just published in Science from my group, where we actually created the first, or one of the first, I guess, world delocalized self-driving labs, okay? So we call this project ACDC. And what we did in that project is actually build a lab with a bunch of different collaborators around the planet. The whole point was to generate extremely expensive data points for an application called organic lasers, okay? And for that, we needed to build an infrastructure that handles such data, right? Where is experiment going to be done? What are the white powders that we're shipping from one place to another in the world? Where are the syntheses done, finished or not? And ultimately, we had to ship fragments back to a central location to actually do final synthesis and characterization. And then another location scaled up the materials, and another location tested the devices, okay? So this talk is not about that particular project, but this talk actually, I wanted to have a little detour on that paper, because what happens in the paper is very, very important lesson. For example, turns out that to predict the performance of an organic laser, you cannot use just DFT. Like, an organic laser is a photophysical problem, and the lifetimes of these lasers are not very well predicted just from simple DFT properties. I argue that most of us can do this. Most of us can actually take any kind of decent representation and regress the DFT properties of it. In our case, we got R squared of 0.86. This is a typical R squared for representation to DFT properties. Okay. We did not use the DFT properties as anything predictor for the performance of an organic laser. We had to actually use the latent space of those for the experimental Gaussian process optimization. It was the representation there that mattered. Okay, you see, as I'm telling you, first data, then representation, and this is a learned representation. But also, okay, how do you do it? So we show, and we're about to put a paper on the archive. It is submitted to NeurIPS, okay? And it is in my desk, that's why it's not in the archive. But what this paper is doing for final edits, what this paper is doing is showing that how ranking, okay, rather than regression is preferred for a lot of material science problems. What do you mean by that? Our model, the equivalent of an R squared is this tau omega quantity. This tau omega is actually 0.9, okay, which is really big compared to about an R squared of 0.6 for our organic laser property. It's easier to predict if a molecule is better than another molecule than the exact value of how much. So I recommend you to predict pairwise rankings, okay? That's something that you can check out more details on that science paper here. And also you can check out more details in the specific paper that we wrote about that is going to be in the archive very soon. Now, after we had that latent space, we need to actually do a Bayesian optimization over it, right? So we had a chemical space of about 190,000 computed molecules. Turns out those were the molecules that a robot could also synthesize. So then we were able to do a Bayesian optimization, okay, over that particular space. And the Bayesian optimizations that we use here in material science contain continuous variables, discrete variables, and usually are multi-objective. So my group has worked very hard on developing algorithms like Phoenix, Griffin, and Chimera that allow you to do algorithmic Bayesian optimization to make sense from material science. So I told you that data was king. Well, in this particular case of a chemical space of about 190,000 molecules, that is a combinatorics of all the fragments that we could do, we were able to actually synthesize about 1,000 molecules. Our record rate was about 500 molecules in 3 months. This is very, very hard chemical synthesis. But if you take a look at how much this cost, okay, for the entire DARPA project that we spent on this, 5 years, several different research groups, this is about $10,000 per data point. Of course, this contains the salaries, the equipment, characterization equipment, etc., the shipping costs, etc., right? Conference travel of about the entire team that actually built this, right? But that gives you an idea why I think data is the most important thing in machine learning, okay? This is an example of why these neural network embeddings are important. This is a lesson about representation. If you actually correlate the fingerprints of a molecule against the laser properties, you get basically no R. But if you predict the actual embedding, you get about an R of 0.43. Again, that's an extremely simple, barbaric way of correlating things, but gives you an idea that there's some signal in the learned representation that we then exploit with further work with our Gaussian process and ranking algorithm, right? So this is what happened in this paper. We were able to basically scan the conditions for these chemical reactions, then carry out a hypercube sampling, which is basically a statistical stochastic grid over the data points that maximizes the diversity of the data points. That actually helps us feed a proper Bayesian optimizer that allowed us to find some of the best laser molecules in the world. This green line means how many materials are best in class, okay? Better than anybody else in the world. So we're able to show that we're able to come up with materials that are best in class over our baseline, over our previous paper, okay? This yellow one is another paper of ours. Sorry, this blue one. So this is over a paper of ours that was before, or then over basically before us. So this gives you an idea of more or less our improvement in terms of how many experiments you need to actually start making some damage in material science optimization. So now to end this idea that data is king, well, if you actually look at the this UMAP of those of that particular representation and where the good lasers are, you can see this cow here, and in the bottom of the cow you get the best data points. Okay. So now we talked about data, and now we're going to talk about more about representation, okay? So you're going to pick a representation wisely, right? The representation has to balance scalability and complexity, right? But that is the context of the bitter lesson, okay? So I'll give you one example. Many of you know the smiles, okay? So smiles are a great representation for molecules, but the problem of smiles is that smiles are invalid. If you actually, most of the smiles that you will ever write will be invalid smiles because they will not follow the grammar rules of smile. Whereas in my group, we developed a representation called selfies that is now very heavily utilized by many others. And it's as simple as that loading a Python package and converting a smiles representation to a selfies representation in a single line of code and vice versa. But what is the magic about the selfies representation is the selfies representation is 100% valid. If you shuffle any selfie string, the selfie string will be a valid representation. Of course, it's not unique because transversing a graph with a line is never unique, right? There's many ways of transversing a graph, but of course, the idea of the selfie strings is that any generative model or any machine learning model will be able to generate them without worrying about their grammar, okay? So that's why selfies became an extremely popular representation. And just to tell you why it's so important, in this Nature Communications paper with Daniel Flamshepard, we show that pretty much everybody that uses smiles, every method that uses smiles, or in this case, Regina Barzilai's junction tree variational autoencoder combined with the smiles representation will fail to represent very, very large molecules. This is actually protein-sized molecules represented atom by atom, okay? And selfies, right, can generate this because selfies are 100% valid. Because you have a failure rate for characters, characters are coming up at a very low and low and low and low error rate, but still everyone in a while, when you have thousands of atoms, you're going to fail. Whereas selfies, which is a representation that is 100% valid, can actually be scaled all the way down to proteins, atom by atom, right? So this gives you an idea how selfies as a representation is better than smiles. So first concentrate on the data, then concentrate on the representation, and then you can make progress. Now, it's too bad I cannot see you guys in the audience, but I would like to know how many of you know what the bitter lesson is. You can see here a Negroni, very nice bitter drink. So the bitter lesson is work, actually raise his hand. The bitter lesson is work by Rich Sutton, okay? It's Rich Sutton, one of the founders of reinforcement learning, and you guys can read the quote here, basically talks about how in computer vision, in language modeling, everywhere basically, where machine learning has been scaled, the most elegant representations that people actually come up with, super fancy representations that are actually, as he calls them, human-centric, are replaced by the representations that are easy to scale, okay? So we, in physics, we have to have balance, right? How much physical information is in our representation, or how complex it is, versus how scalable or easy it is to actually work with, right? And it's going to be that kind of bitter lesson that is not necessarily the case that the most elegant method will always win, that I really want to disseminate in the field of material science for chemistry, because many of us are working on very complex representations. So this paper, which should be published very, very soon, okay, Daniel and I have had a slow time going through the review process, and it's our final review. Hopefully it appears very soon. Shows something very sexy, right? We took GPT, but we didn't do ChatGPT. We just took GPT, the GPT model, okay? And then we trained it on literally XYZ, CIF, and PDB files tokenized, okay? So we tokenized the chemical structure coordinates. Notice how this has no symmetries, okay? It doesn't contain any kind of elegance. It is literally the XYZ input file, okay? Or CIF, or PDB, okay? And we're able to show that we can generate protein pockets, we can generate material science databases and molecular databases with the same sequence model trained on this simple input file data, right? So read more about this in the paper, but we get some of the state of the art in some cases. And this basically tells you that, perhaps scaling a model like this is going to be way easier than scaling complex models, right? And now I told you finally in this set of recommendations, the evaluation is very important. Especially in molecular science, people were using this very simple penalized log P kind of like metric that Benjamin Sanchez-Lengeling and me and others introduced very early on with Rafa Gomez Bombarelli as well as part of early papers that we published. So people were actually optimizing very sophisticated methods on very I would say, simple or even shitty benchmarking. So if you want to generate a model, you want to think about how to benchmark it. So we got this paper accepted in Europe a couple of years ago, where we actually show a library called Tartarus, where we actually show real applications like organic photovoltaics, organic light-emitting diodes, protein ligand binding, and chemical reaction substrates. The platform actually can call codes to actually verify. And therefore, now you can actually benchmark your algorithms with real data sets that make more sense to us. For example, predicting the emission of an organic light emitting diode, which is a problem that I showed you from the Gomez-Bombarelli paper a long time ago. But you can actually see here how our genetic algorithm beats AstraZeneca's generative model, for example, right? Or here is another genetic algorithm beating AstraZeneca's generative model, right? Here is a simple LSTM on our selfies, for example. And you can see here how our selfies BAE, for example, is better for a particular application, right? But this kind of gives you an idea of how we think about benchmarking, right? We think about benchmarking in proper data sets. So some of you know I'm very excited about self-driving laboratories, right? So I believe ultimately things that matter are how to accelerate discovery, right? And so many of us in this room, I guess, are very excited about the idea of taking our AI and instantiating it in the world, right? Making the AI make safe and sound decisions, and safety is very important. We're very interested in safety nowadays. How to make quick decisions that will allow us to actually accelerate materials discovery, okay? That's what self-driving labs promise, okay? And in this particular case, as I showed you in the organic laser example, we're able to demonstrate that self-driving labs actually can discover new materials quite well, right? So this talk will not be obviously the same without talking about language models. Of course, they're extremely important. We're all using them for one thing or another. So I just want to show you this paper called Orana that my group is also about to be accepted, hopefully, that actually integrates language models and robotic execution, experimental planning, and a bunch of other modules. This is not just an LLM. It's a bunch of modules integrated with an LLM to actually have a talking robot that does science. So let me just show you a video of how Orana works here. Let me know if you can hear the audio.
I don't think we can.
Really? Oh, shit. What am I gonna do? Well, because I wanted at 12:45. Usually works. Let me see. Maybe I can reshare.
Yeah, you should try to share with audio.
Yeah, let me stop sharing. I did share with audio for some reason. Share sound. Um, the issue is probably, you know, as I told you guys, this is a new machine. So
Yeah, so in the share options,
yeah,
there's like an advanced tab, then there's computer audio. That should be the one.
yeah, I put share audio, okay, which is basically it's a little bit new, like advanced. Okay, let me go to advanced. Yeah, if I go to advanced, yeah, it's video files, lights at the background, etc. They changed a little bit the zoom, but I know what you're saying. I want to share my entire desktop just to make sure it works. Sorry if you guys see some sort of emails or something. I hate when you know suddenly an email shows up or something. But yeah, I'm worried about that. There's a term sheet there. Okay, here it is. If it doesn't sound well, so be it. Can you hear? Could you hear that or not?
No, still nothing,
Okay,
unfortunately.
never mind. So believe me, my student Marta is talking to this robot called Organa. Okay, back and forth, and this is kind of sad that you cannot hear the audio, but back and forth, Organa is asking Marta different questions about the experiment setup, right? Questions that have to do with when does experiment start and end. And you guys, of course, can just Google Organa and my name, and you will find the video. And what's very nice about this paper is that the robot also has computer vision, right? Which is very important for these arms to be able to actually identify the three-dimensional environment they're on, so you don't have coordinate-based robots. So in this particular case, you can actually see the robot asking Marta, what exactly is this thing that is in this bounding box, so it can actually carry out the experiment.
That is the washing beaker. What will this be used?
So the robot is asking Marta what to do, and eventually our planner starts carrying out the experiment. Okay, and you can see here all the different parallelization. Actually, we even have a parallel compiler that knows how to run things in parallel while the robot is doing the experiments. And obviously, this robot is doing a simple electrochemistry experiment and combines arms with pumps. Okay, so it's kind of like a simple demo of how the robot that we call Organa will actually be fully expanded. But what is very important about Organa is that it's all modular, right? We're able to actually add more modules, for example, electrode polisher or this or that, and make it more and more powerful. So my group expects that if many other groups around the world together with us start creating more Organa modules, then we will have different instances of Organa doing different experiments around the world. And of course, this could not have been done without the power of agentic methods and language models and things like that. You can actually see here our clarify verification of the conditions algorithm. You can see here our LLM machine, but also you can see here a lot of robotics things that we had to develop. Hardware developments and also algorithmic developments, for example, pouring skills for robotics, right? So now I'm running out of time. I have like only 5 minutes because I want to have 15 for questions. So I'm gonna just tell you some rules that I came up with, and then I found out George Whitesides came up with similar rules for his own group. And one time we were in the hallway discussing how we run research, and then the combination of the rules is what I now tell my students. Okay, so I call them the Aspuru-Guzik Whitesides rules for significant research projects. The most important one for me is, has the problem been solved before? If the answer is no, why are you working on it? I'm serious. Like optimizing somebody else's previous result is kind of nice, but it's not as impactful as doing something completely new. So if you can do something completely new, go ahead and do it. Question number 2, is a problem relevant to society with climate change, pollution, water filtration issues, etc.? The more and more you think about how to help society, the more important your research problem will be. And question number 3, is it remotely possible? My group and I like to work at the edge of imagination, where the problem is actually hard and barely doable, like Organa itself, for example, right? It's very hard to integrate all of those things and create a robot that talks to you in English and actually carries out chemistry experiments with computer vision and everything integrated. That's where we want to be. We want to be at the interface of what's possible or not, and that will also make your research more impactful. Okay? So now, those are the 3 recommendations that my group and I follow, okay? Your mileage may vary. Your group might have other ones. Many groups nowadays, the only thing they want to do is try to beat the previous group by 0.0001 performance, especially in machine learning, and I find that boring. But there's 3 ways I think that you can achieve impact in machine learning for chemistry. First, you can achieve impact by breadth, then by depth, or by scale. Those are kind of like the 3 kind of like main ways of doing it, okay? So breadth is go somewhere that nobody has been before, okay? In chemistry and material science, okay, come on, there's photochemistry, nuclear science, spectroscopy, astrochemistry, okay? It's a very chemistry-oriented talk, but in material science, it's the same thing. Think about problems that not too many people are on there. And that will allow you to do cool things. For example, this is one of my favorite papers in my group. Rotational spectroscopy, right? This is a very powerful tool, right? Molecular rotation spectroscopy. There have been 0 machine learning models, okay, before us, 0 machine learning models that predicted the molecular structure from the rotational spectroscopy, okay? So if you do what we did then, you have the baseline. Like now everybody has to compare to your baseline. So that's the best thing. If you do breadth, you will end up in weird places like rotational spectroscopy and build the first algorithm for that particular application. So that's, I think, where you want to be. The second thing, obviously, is depth. Okay, I'm going to use back our example of the organic lasers. Go all in, right? We spent $12 million of DARPA money, 7 groups around the world, or 6 or 7 groups around the world, a 5-year collaboration, and we're able to develop the best organic lasers in the world. There are these molecules synthesized by all these different robots around the planet. Okay, and that's a depth project, right? That you're going in all in, right? So if you want to also solve a problem, you might want to spend years going on it. Okay. And finally, scale. More and more people get depressed because big companies have a lot of scale power. So academics can also compete with the national supercomputers, but a massive model that is accurately in general. For example, this OpenDAC dataset for David Scholl and Zach Ulisi, right? This is basically a MOV dataset that contains 39 million DFT calculations, right? Or the recently developed OR force field by Orbital Materials are examples of very big data type problems, right? So you can also win by scaling in certain cases. And my final piece of advice, try to make a multidisciplinary group, work with computer scientists, chemists, material scientists, chemical engineers. That's how I structure my group, and that's how I think we've been quite successful. But in general, if you lack expertise on something, actually go talk to the expert and work together to build something bigger that you could build on your own. So what's next? I believe what's next is going to be an AI scientist, right? We're going to have a robot or an AI that actually makes its own decisions. But what do we mean by that? Okay, that's controversial. So we spent a lot of time thinking about the philosophy of this, and I want to tell you about two philosophy/papers, right? We need to think about the philosophy of what things mean before we actually can make progress. And this particular case, in this paper led by Mario Kren, and now junior group leader at the Max Planck, and many other group members, we actually came up with 3 different ways that computers are used to do science. Number one is the oldest one, is computational microscope. You run the simulation and see what happens. Number two is the data-driven approach that we all work on. But number three is the computer understanding and actually telling you what happened and proposing new hypotheses. Number three hasn't happened yet. I mean, if it has happened, let me know in the questions and answers. But really, when I made a survey of 80 scientists around the world, nobody told me the computer really was an agent of understanding. So we came up with a Turing test, okay, to actually test if scientific understanding will have happened, and an artificial intelligence will have gained scientific understanding if it can predict the qualitative consequences of a theory, and then use them in a new context. And finally, transfer them. Like it should be able to teach another person what it learned. Okay, and those are the conditions that my group and I think are very important and kind of as a Turing test for an AI that understands. So we just published our first paper, okay, on philosophy with an actual philosopher of science, and Zijian Zhang, okay, my student, is very brave to combine a chemist, a philosopher, and a physicist in a room to start thinking about how to build AIs that actually understand things. So I actually, because I'm running out of time, I invite you to download this paper from the archive and learn a little bit more about how we think about understanding, okay? So now some of you might be depressed and say, oh my God, but AI is going to take over? And the answer is not, right? We are the God behind the God. In this poem of Borges about chess, he says, God moves the player and he the piece. Which God behind the God begets the plot of dust and time and dream agonies. So in that chess game, there might be a God moving the player, but we might be the God behind the God that moves the player, right? We're going to be building these systems that do scientific discovery. And with that, I'm going to advertise the journal Digital Discovery very briefly. Okay, I really want everybody to submit their best work there. Impact factor of 6.2, open access, data reviewer. We need data reviewers. So if you're a postdoc and want to be a data reviewer of code and data, you believe in FAIR, please enter this data reviewer website here and become a reviewer for Digital Discovery. And with that, I'm going to open up for questions. Thank you very much for your time.
Thanks, Alán, for an excellent talk. We're now open to questions. You're welcome to unmute yourself at this time and ask a question, or if not, you can ask in the chat and I'll ask for you. Any questions from the audience so far? I'll start then. What kind of challenges do you see in adapting this approach for self-driving labs to material science?
Well, I mean, the most important thing is characterization. You want to make sure that when you characterize a material, right, the material actually is the right material that you synthesize, right? I mean, there have been recent examples where this has been a problem, and I think it's very important what I mentioned, the multidisciplinarity there, that you work with domain experts and you make sure that the experimental domain experts actually are involved in what you're doing as well. So I think that's one challenge, and one that started to happen is safety. I recently was visiting a university that will remain anonymous. where somebody told me a theoretician came up with some synthetic conditions, went into an oven and tried them, and the oven exploded, right? Because he was not an experimentalist, he didn't know the constraints and ran just the AI generated conditions and generated a lab accident. So we have to be very careful about the self-driving lab also killing somebody or creating something dangerous, a dangerous molecule. So I think safety together with characterization are some of the biggest challenges.
So would the safety perspective be guided by AI as well, like having an experimentalist kind of encode rules for general safety procedures in the synthesis part, or sort of
Yes,
human review ultimately?
I think both of them. I think it has to be both humans and AI. I think a human always has to supervise their AI models, right? You don't want to let them rogue, but I think it's very important to have humans in the loop. But definitely, my lab started working along these directions with a paper called Clarify that actually at least makes sure that LLMs generate valid instructions. We want to extend it to safe, valid, and safe instructions. And I think the more and more we enable robots like Organa to do more and more sophisticated chemistry, we want to make sure they don't blow up the room or kill the operator or do something crazy like release a gas.
Yeah.
Yeah.
Let's see. We have a question from Adam. Great
Mhm.
talk, Alon. Appreciate the insights. How do you know now is a good time to convert research to product? Second question, how much of these material AI startups, there are many, are effectively privately funded research? And third question, how do we know value can be delivered to industry?
Good question, Adam. Absolutely. Who am I to talk? I co-founded Kevotics in 2017. So the lessons that we find from Kevotics is, yes, we can provide value to the chemical industry by providing AI capabilities and data science capabilities. That's what the business model of Kevotics is. I agree. It's an incredible amount of money raised. I mentioned orbital materials, but it's also COSP AI and Radical AI and many new companies that are actually raising a lot of money to try to do AI for materials. I think it makes sense that venture capital is also involved. But of course, the warning to those companies is to be quite humble and to really believe in characterization and believe in safety and these kinds of things. And I am more optimistic, Prameya, that this is beyond just publicly funded research projects. This is a practicalization of what we do in academia. And I am cheering for those startups. I hope they succeed, all of them. There's a space for all of us.
Great. We also have a question from Uni. How do you think about AI approaching materials with unclear active sites? For example, heterogeneous catalysis, where active sites evolve dynamically under reaction conditions. And what does this look like to you?
Well, to, it's hard to know exactly how to approach that. For example, you can imagine having an ensemble model. My former student, now professor in Toronto, Benjamin Sanchez-Lengeling, did an AI model for mixtures of molecules, okay? Very interesting model for perfumery. Like if you want to predict how a perfume smells, you don't need to predict only one structure to property. The blend contains a lot of smells, right? So a catalyst, I imagine, is basically like a blend, right? It's moving around. It has an active site in this conformation, an active site in another conformation, etc. So it's a blend of performance of different basic models. So maybe you want to look at what Benjamin Sanchez-Lengeling and my student Gary Tom and others have done on this kind of blending models. So I imagine a model that contains many models, many can able to represent many different active sites, for example. You can also simulate that with machine learning force fields. We have a paper with Nuria Munoz on some graph networks for catalysis. So it's a very big field. So if you send me an email, I'm happy to answer something more specific. But I think there's ways to go around this problem. But maybe what your question goes is, okay, Alan, some of the things that you show are simple, right? But catalysis is very complex. Like it's always complex. The organic laser, even if it's a single molecule, is extremely complex problem in solution, right? Very humbling. Or the molecular spectroscopy problem. So it's always hard, right? I think it's just the fact that as soon as you start capturing the details in your model and actually are slow and deterministic about it, you can make progress.
Great. A question from Johanna. Thanks a lot for the nice overview. Do you think these methods will pose a threat to the chemical industry in the next 5 to 10 years?
And Johanna, I don't know what you mean by a threat. I think they're an opportunity. The chemical industry is digitalizing themselves as well. Just last few months, Baby, the Bayesian optimization package by Merck Europe was released. Then Pfizer in the US released theirs, and also BASF in Europe released theirs. So I know at least of 3 Bayesian optimization packages released by industry. They're all working. I know that the baby people went to visit the people from BASF. So I know they even work with each other. So I think they're part of this community. Just in the Faraday discussion I was before, many people were working on this, both industry and academia. So I don't think it's a threat. I think academia will adopt this, industry will adopt these things, and maybe some of these startups might make a niche to themselves. I think you wanna also emphasize that the chemical industry owns the plants, so it's gonna be very hard for these startups to completely beat them up, because ultimately you also have to build plants to make the chemicals. So I think we need to work with them.
Great. What kinds of like open sourcing are you doing for your models? Like, are yours fully open source versus like these private industry ones, which I'm assuming are generally closed sourced IP?
Everything that the Matter Lab does is open source, pretty much. I have my companies, right? Zapata, Robotics, Axiomatic, and Intrepid Labs. Obviously, what we do in the companies is stay in the company. That's where the company is built.
Yeah.
But the data that my lab does and the Acceleration Consortium does is open. All our designs are open. We release things in Nature Protocols. We're about to submit a paper to Nature Protocols for a first protocol for our synthesis robot. And if not, of course, our Journal Digital Discovery, we release tutorials. Yes, of course, as like any open source software, you release it, and then sometimes you don't maintain it very well, because my group is not really maintaining up to date all the codes that we ever developed. But they're out there in GitHub and so on, and you can just download them and GitLab and play with them. That's I think how we'll all learn.
Yeah, obviously speaking with the bias coming from MP, but I think that's a huge advantage that you at least have in the academic space over the industry spaces, open sourcing and making this equitable to everybody around the world. Another question from Apramea. Hey, Alán, thanks for the insights. When you talk about the importance of quality data in chemistry, is it only about the experimental data or also data samples generated from these up-and-coming generative models? If we use the synthetic data, how can we properly evaluate that? And then what are your opinions moving forward?
Yeah, of course. Experimental data is better than generated with model data, for sure. If you can generate data with your robot, you should do that, obviously, right? But generative model data is important because it can allow you to actually make decisions. I'll give you one example. It's not generative, but it's an example. We recently published a paper in Chemical Science within Silicon Medicine, where we use AlphaFold to predict the structure of a protein that we don't know the fold of, and use our generative models to target it as a drug ligand combination. And we found a good lead candidate for liver cancer, right? That's an example where digital data was actually used for a particular screening project. So those digital generative models might be useful for you to actually, in silico, make some prediction and then synthesize it.
Great. A question from Carlos Andres. Regarding depth versus optimization, isn't it that synthetic reaction space needs to be automated or optimized before depth can be achieved?
Can you repeat the question? Sorry, I was replying to one on the chat. I couldn't resist.
Oh, no
So,
worries.
sorry.
So regarding depth versus optimization, isn't it that synthetic reaction space needs to be automated or optimized before depth can be achieved?
But I don't know what they mean by depth. Well, I mean, no. I mean, the way we achieve depth in my group is we explore chemical spaces that a robot can do. So we design a chemical space that contains molecules that we believe are going to be highly valuable. Then we build a robot that can make molecules in that space. And then we only screen and generate and explore molecules that can be made by the robot. So that is how we build a self-driving lab that is successful. If you want to just a random generative model, give you a molecule, and then a robot randomly synthesize it, you're going to be in a lot of trouble because robots are not able to make an arbitrary molecule. They're only able to make very few reactions. You have to have the symptoms for it. And therefore, at this moment, it's not possible to have a generic model robot make a generic molecule.
What kinds of like targeted spaces are you focusing on then for
organic
synthesizing?
flow batteries, organic lasers. Those are the main ones, but I collaborate with people on nanoparticles. I collaborate with people. Actually, that's not true. Drug formulations is a big space where we can do that as well. And we have a company called Interactive Labs working on that.
Great. Question from Roshi. I found the 3 rules of selecting research questions very insightful. What, in your opinion, are the research directions that can combine breadth and depth and scale with the power of AI?
I don't know, Rushi, like it's very hard to cover 3 at the same time, right? You might pick depth and spend 5 years like I did with my collaborators just working on depth, right? So, but I think if you think about that 3-dimensional optimization, a little bit as a Pareto frontier or a hypervolume, you want to maximize the hypervolume of depth, breadth, and scale, and try to have your project be as broad, as deep, and as scalable, right? But usually you just pick one axis and go that way, right? At least for a paper.
Great. I think if we don't have any other question, oh, okay, sorry, one more question. You kind of answered this as well, but do you have any advice from your experience? Oh, sorry, for a person who's trying to build an orchestration software for their self-driving lab, and what should you prioritize?
I was telling that's the person I was responding on the chat. The person is Mert Ozan. I told them that we, in particular, in my lab, developed ChemOS 2.0. It's an open source orchestration lab, and I think the more and more we all start using the same software, the more and more we don't reinvent the wheel. So I invite him and others to read our recent chemical reviews paper on self-driving labs. There we actually cover many of these softwares, but I think build on top of one and don't start from scratch. I think starting from scratch just wastes your time.
Are there any kind of like data or infrastructure standards as well that are being developed with ChemOS to kind of standardize how these things are, interpreted and output?
ChemOS is just used by us at the moment, really. That's a sad story, right? Like every lab just decides to build their own orchestration system. And like the good news is that we have a $200 million grant here in Toronto called the Acceleration Consortium. And we're going to try to standardize ChemOS across the 7 self-driving labs that we're building. So hopefully that will actually make it more like robust. The Japanese are incredible. They have something called NIMS-OS, and they also have worked with the vendors, so they have standardized the input and output formats for the vendors. So if you want to buy a robot to do chemistry, turns out the Japanese vendors already have standards, thanks to this automation effort. So I just found out, it's just not very well publicized, but I was very impressed by all these Japanese materials companies that already have these kinds of standards.
Great. Okay. And then, sorry, one final question from Ferris. What about AI for gas storage, like carbon dioxide capture? Is there some startup or lab that are specifically working in this field?
Yes, Faris, the company is called Cosp AI. They're hiring. This is very cool people. Baron Smith is one of the co-founders, and Max Welling, the other one. I've talked to them. They're pretty cool. They're doing CO2 capture using metal organic framework. So if you're looking for a job, apply there. Yeah.
Great. Thank you again for an excellent talk. This is fantastic. And thanks.
Thank you, everybody. I see more than 100 people connected. I'm honored that now there are 64 left, I guess, but I'm honored that you guys were here, and thank you very much for everything.